Well, I'm terribly sorry to disappoint you, but I made a mistake at the end of the last recording. We're not actually quite done with capacitors yet. I have said several times when I was discussing capacitors that the two metal plates that make it up are not electrically connected to each other. And I said several times that, in fact, usually there's some sort of an insulating material placed between the plates. And you might have thought that the reason for that is to prevent any electrical contact between the two plates, but it turns out no, that's not the reason. There's a far more interesting issue. So I'm going to describe that here, and I'm going to make a schematic drawing of the capacitor rather than trying to be a little more realistic here. Hopefully you're comfortable enough with capacitors now to be able to follow this. Okay, so here's the top plate, here's the bottom plate, and we'll connect them through some potential source, again, a battery or whatever. Okay. But the new thing that I'm going to do is I'm going to put some sort of insulating material between the two plates. And I've said before, this stuff is usually a wax or a plastic or Teflon or something. I don't know about Teflon, but anyway, some sort of insulating molecule. To start off with, by the way, time for a new vocabulary term. The cool physics name for insulators is actually dielectric. So I'm going to talk about dielectrics. And capacitors. So a dielectric is just, as I say, a fancy word for insulator. And the key physical property that matters here is, well, there are two. One, remember that an insulator, the thing that makes something an insulator or a dielectric, is that the charges that make up the dielectric material cannot move. In a conductor, the charges move really easily. In an insulator, in a dielectric, they don't move basically at all. All right? So there are charges inside this slab of dielectric, but they're fixed in place. They can't move. So let's think about it. So we charge up the capacitor, and the bottom plate, the way I've drawn it here anyway, the bottom plate ends up with an overall negative surface charge density. The top plate ends up with an overall negative surface charge density, equal, assuming that the areas of the plates are equal, then the amount of charge is equal, and therefore the charge density is also equal. Okay, and so far so good. And this sets up, as you know, an electric field. And the electric field, due to these capacitor plates, points away from the positive plate and towards the negative plate. But before I finish drawing this, sorry about this. I'll put these back, so you don't have to erase yours if you don't want to. This dielectric material, though, I said it's made of some sort of material where the molecules, or the material that make up typically molecules, they can't move. They're fixed in place. Something like this. Well, so then we charge the capacitor, and as I was starting to say, there's an electric field that gets created. And it passes right through the dielectric material. Okay. And the result of all of this is a large electric field pointing this way. Now, this electric field, of course, will apply a force on the charges inside the dielectric material, as it will, as any electric field would apply a force on any charges. Okay, and as I said, these molecules, these molecules made of charged particles, they're not going to move because it's a dielectric, it's an insulator. However, as we've seen before in other contexts, although these molecules won't move, they will rotate. Okay, and so we will get an induced charge distribution, and essentially the negative charge of the top plate will tend to attract the positive side. And now I'm going to clean this diagram up a little bit. The negative charge on the top plate will attract the positive side of the dielectric molecules, okay? And so they will tend to rotate so that their positive ends of the molecules of the dielectric are somewhat closer to the negative plate than they are to the positive plate. And exactly the same thing is true in reverse on the side of the dielectric near the bottom, near the bottom plate, which is positively charged. So the bottom of the dielectric slab picks up a slight negative charge. Now these aren't huge, but they're there, and they aren't huge, but they are significant enough that they create their own field. So we have what? We have a field from the capacitor pointing straight upward. And we have this induced field, if I can call it that, that's pointing away from these induced positive charges to these induced negative charges inside the dielectric, okay? And it's pointing in the opposite direction to the capacitor field. And the result of all of this is that the net field inside the capacitor between the plates, the net field has been significantly reduced. Okay? So inserting these slabs of capacitors typically go from plate to plate. They're physically touching both plates. So this new field, this induced field, fills up the entire space, and it tends to cancel out the field of the capacitor. But if you decrease, it doesn't cancel it out completely, but it does reduce the overall field. But if you reduce the overall field in here, you've also reduced the potential difference between the plates. And if you reduce the potential difference between the plates, it's now gotten smaller than what the battery is, and so the battery can still pump more charge. And so the result of doing all of this is that the amount of charge you can store in a capacitor with a slab of dielectric is larger than the amount of charge that you can store in an otherwise identical capacitor, but without that slab of dielectric. And so the whole point and purpose of a dielectric is to give you a cheap, and I mean cheap in terms of money, a cheap and very easy way of increasing the capacitance of the capacitor, allowing you to store more charge and or equivalently allowing you to store more energy. And this is how it does it. Again, the key point is that the field of the capacitor plates creates an induced field in the dielectric material, which tends to cancel the capacitor field, reducing this potential difference compared to the potential difference supplied by the battery, and therefore the battery is able to dump more charge on it. And so that's the physics behind it. And in the next recording, we'll walk our way through the calculations. How do we calculate all this, and can we describe this in some sort of mathematical concrete terms? And the answer is yes, but we'll have to define some concepts, and so that will be coming,